Well, I'm not happy with the number of people that are in the lecture. Again, all of you are doing the correct thing by being here, but let's get started. First off, are there any questions? Okay, I don't hear anything. I'm also wondering, can someone say something to just check whether my headphones are connected?
Hello?
Okay, thanks. Good, they are. Right, so let's get started. What we're going to do at the beginning is we're going to think like a physicist. And physicists have a reputation among mathematicians for doing things in a very hand-wavy manner and not being rigorous, i.e. Intuitive hand-waving justifications. So before, we had this result about the area between two curves. Between, let's say, the graphs of f and g. And this was justified by Cavalieri's theorem. So we had some sort of justification for it. And then similarly, we had some justification for this idea of doing area by slices. So these results respectively said that we could imagine taking our function, let's say this is our f and this is our g. And we could write it as a bunch of these are vertical slices with heights f of x minus g of x. And then the idea was that we were summing up the heights of these slices. But Cavalieri's theorem told us that we could translate all of these downwards if this were just the function f minus g. And then we know that an integral gives us the area under the curve. So we can justify it in that regard. A similar justification holds for finding volumes by slicing. And so we can say that these results, let's call this result alpha, let's call this result beta. Alpha says that area is equal to the integral from the bounds, let's say a to b, of h of x dx. And beta says that volume is given as the integral with, let's just use the same letters for the bounds, there are some bounds, of area of, let's say, x dx. But then we had a third result, gamma, and that was this cylindrical shell method. And the picture for the cylindrical shell method was, imagine that we had some volume of revolution. So imagine that we take a function that looks like this. And then let's say that this is our y-axis. This is our x-axis. We reflect this. And then we take a surface of volume of revolution. So for example, if we have a certain height here, x, negative x, then what happens is we get shapes that look like this. I mean, overall, the function looks like, so this is known as a cylindrical shell, what's pictured. And the area of a cylindrical shell, A of x, was given as, does anyone remember? Let's say our function is f. So it's the circumference of the circle times the height, right? What is the radius of the circle?
Pi.
Well, pi is like some absolute constant, a circle constant, right? So pi comes into the calculation of the circumference, but the radius has something to do with these values x and f of x.
Oh, x.
Yeah, so x is the radius. So what's the circumference?
2 pi x.
Exactly. Now, that's the circumference of the circle. And what's the height of the cylinder?
F of x.
Exactly. Good, thanks. So that is the area of a cylindrical shell. And then the result gamma said that the volume would be also given as the integral from a to b. Let's say these are the bounds on x. All of these are just bounds corresponding to the situation of a of x dx. But one of these is not like the others. In this one, we were taking slices. These were level slices. But these are not level slices. So you may ask, is this formula correct? Well, a non-proof that this formula is correct, but some evidence that this formula is correct is, for example, if I go to the lecture notes from last time, so these were the notes from last time, and I look at what I did at the end of the lecture, we had some problem. It was this problem they were touching, and we did it in two ways. We first did it using cylindrical shells, and then we did it using washers when integrating with respect to y. And we got the same answer in both ways. So that doesn't prove anything. That could have just been a coincidence, but it provides some evidence for this formula being true. So why then we're going to ask today, we're going to begin by doing a physicist justification for why this formula holds. Let me just set this up already. And before we do that, we're going to justify these other two formulas. Well, at least we're going to justify alpha. So suppose that here are some justifications. And by the way, the reason that I'm doing these justifications is because arguments like this are important, and there are the type of arguments that I am supposed to be showing you in this course. And also because we're going to use these arguments to derive two very interesting other formulas, which are not at all obvious. And so in order to understand why the not at all obvious formulas holds, you need to understand how physicists would justify writing things like this. So let's start off first with this alpha, this example, where let's say these are our axes. Let's say this is A, this is B. Then we have one function. Then we have another function. And now imagine that I take the interval A to B and I partition it. So let's say that A is equal to T. I'm going to use T for the indices of the partition. T naught is less than T1 is less than dot, dot, dot is less than Tn, which is equal to B. And then let's say that between T0 and T1, I choose a point. And I'm going to call this point, I'm going to call it S sub I. So choose points Si with Ti being less than Si being less than Ti plus 1. So let's imagine then that we take our A to B, let's say we partition it into, in this case, 4 pieces. And then we choose some point in each interval. Then what I'm going to do is I'm going to take this point and I'm going to look at the slices over this point. And then I'm going to form rectangles corresponding to these slices. So here to here, here to here, okay. Yeah, drawing is hard. Okay, you get the idea. And so this is going to be an approximation to the area. So what I obtain is that the approximate area, A approx, is equal to the sum from, let's say, I is equal to 0 to n minus 1 of what? So first I'm going to take these S sub I range from 0 to n minus 1. And then I'm going to take the height f of S sub I, and I'm going to multiply it by delta t sub I, where delta t sub I is t sub I plus 1 minus t sub I. So it's the difference between successive things. So this is the approximate area, right? If I choose some points, I get like this, I get an approximation. We're not taking any infs or subs right now. We're taking the height by sampling at some point. And the physicist's justification is that as we make this finer, we get the area. This should approach the area. With finer partitions. And so what happens is then that the area is the sum changes to an integral from A to B. The f of S sub I, well, S sub I is this point in the middle, so that just becomes the variable of integration, x, and the delta t sub I becomes dx. So a physicist would look at this formula and then they would just write this formula directly translating from it. Because as you make it finer, this approaches exactly the integral given how we defined the integral, right? Any questions about this justification? Okay, let's move on to the next one. And I'm now going to do gamma. I'm not going to do beta, but we want to justify the cylindrical shell method. So what happens when you look at a cylindrical shell? Let's say we take our interval here. Let's say that this is A and that this is B. And now we are going to cut it up into some number of pieces. I previously, let's say 3 pieces in this case. And that's, we're going to choose some point in the middle of these pieces. Now what we're going to do is we're going to take the height over this point. And we're going to use that to form a 3-dimensional cylindrical shell. So it's going to be a shell with some thickness now to it. Can everyone picture what I mean by this? So we're going to take this interval along the x-axis, and we're going to make a cylindrical shell of that thickness, taking some point in the middle, sampling it as the height, and forming this 3-dimensional solid. And then we're going to do that for each of the intervals. So I'm going to draw these in some other color. Let's do this red. And then this is already drawn, and then I draw it like this. Okay, now the question is, so the physicist's idea is that when these get finer, this obviously becomes the area, because I'm a physicist and physicists just say things like that and they accept it. So the physicist's justification is that the proximate area is given by summing up all of these cylinders. Now, what is the volume of one of these cylinders? So suppose that we have here, let's just draw one of these cylinders specifically. So suppose that this is your x sub I. This is your x sub I plus 1. Sorry, I'm going to call them t sub I and t sub I plus 1. And then in the middle of them, you've chosen some point s sub I, somewhere between them. And then you've taken the function's value. So this is f of s sub I. And what you're going to do with that function value is that you're going to form a cylinder. So suppose we reflect it. Okay, now the question is, what is the volume of this? So before, when I had this expression, I could write it as sort of delta A I. So for the I piece, I'm getting an increase in area, and the increase of the area corresponding to the I piece is f of s sub I times delta t sub I. So you can imagine that each one of these pieces is adding some area here, and the I piece is adding this much area. Is that clear? Any questions about that?
Can you say that one more time?
Right. So here, I've said that the approximate area consists of a sum of several pieces. And I've drawn the pieces here. And then the question is that we can imagine that each additional piece is adding a bit to the area, just a bit, because the pieces are small. And so we'd like to know how much the area changes when you add one more piece. And so I'm going to call that delta A sub I. That's how the approximate area is changing more specifically. And let's say it's one of these pieces like this one. Then what is its area? It's the height, which is this point s sub I that I'm sampling in the middle, times the width, which is delta t sub I. Does that make sense?
Yeah.
Good. So then the area is the sum of all of these delta A sub I's. Well, here I'm going to have not a delta A sub I, but a delta V sub I. And what that's going to be is it's going to be the volume of this hollow but thickened cylinder. Now, we can find what this volume is by subtracting the the volume of the bigger cylinder from the volume of the smaller cylinder, right? Does that make sense? So what is the volume of the outer cylinder? First off, what is the outer radius? Looking at the labels in this picture.
T sub I plus 1.
Exactly. And so what is the area of the base of if I just look at the bigger circle, ignoring that there's a hole in the middle? What's the area of this base?
Pi ti plus 1 squared.
Yep. Now what I can do is I can actually take the area of the base and multiply it by the height. Let's say I subtract, well, I can do it in two different ways. Okay, fine. Let's just, fine, never mind. What's the volume of the bigger cylinder then, ignoring that there's a hole in the middle? What do I multiply this by?
S sub I.
Exactly. And then if I'm subtracting the whole, then that's going to be minus, and then just the inner radius is t sub I, f of s sub I. And so I can write that as pi t sub I plus 1 squared minus t sub I squared times f of s sub I. But the thing is that also I'm not only am I not happy with this expression, I'm also not happy with the way that I've positioned it on the page. Okay. Now I'm going to take this expression and I'm going to manipulate it. So what's obvious factorization can I do here? Look at this term. What does this term scream that I should do with it?
Take out t sub I.
Well, if what about if I don't want to? Yeah, I could write it as t sub I plus 1 divided by t sub I, but is that ratio really meaningful? So I don't think the ratio is really meaningful. What else can I do with this term? It's something squared minus something else squared.
Can you
What factorization do I do?
T sub I plus 1? No.
Well, yeah, that's that term. And then well, it's a squared minus b squared, right? What's a squared minus b squared? How do I factor this? We all know this. We've already done it a bunch of times in the homework. How can I write a squared minus b squared?
A plus b times a minus b.
Yep. And so I can write this as t sub I plus 1 plus t sub I times t sub I plus 1 minus t sub I times f of s sub I. Now, if I look at this, I can also write this as f of 2 times t sub I plus t sub I plus 1 minus t sub I. So I can rewrite that parenthesis like this. Now, what can I denote t sub I plus 1 minus t sub I as? How have I?
Sorry, can you just go over the between the second to last and the last step?
Right. So if I look at t sub I plus t sub I plus 1, it's this radius plus that radius, right? I can rewrite that as twice the smaller radius plus the difference between the radii. Right? So if you just look at this, it's t sub I plus 1. And then I have minus t sub I minus t sub I. So I get a t sub I. So these two terms are equal. But there's a particular reason that I wrote it like this. That's because t sub I minus t sub I plus 1 minus t sub I can write that in a different way. What's that different way? I referred to it before, right? This is delta t sub I. Does everything make sense? Any questions?
So like which is the preferred, I guess, way? Like would it?
There's a particular reason that I'm writing this, and that's because physicists do this. Mathematicians think this isn't rigorous. The delta t sub I turns into a dx when in physics land. So we're going to massage this into an expression that looks like discrete integral. And in order to do that, we want delta t sub i's in the expression. So I started off with this difference of radii, but look, I've now written it as just the radius, and then here is a delta t sub I, and here's the delta t sub I. So I can write this as pi times 2t sub I plus delta t sub I times delta t sub I, f of s sub I. And so that becomes 2 pi t sub I delta t sub I plus t sub I, let's write it like this, f of s sub I delta t sub I plus pi f of s sub I delta t sub I, and instead of writing it as delta t sub I squared, I'll write it like this, right? So that tells us that the approximate volume is equal to the sum from I is equal to 0 to n of 2 pi t sub I f of s sub I. Well, perhaps I can write it like this. I'll factor the one of the delta t sub I out, plus pi f of s sub I delta t sub I. Oh, laptop is dying. Times delta t sub I. So this is one way that I can write the volume, the approximate volume with respect to these cylindrical shells. And this comes from geometry, right? We looked at what the geometry of a cylindrical shell was. We found what each one of these volumes was, and then we rewrote it and we got this expression. Any questions? If anything's unclear, please ask.
I just have a quick question.
Yeah.
For this, like everything that we just broke down, what would be like the one, I don't know, how would you like define that in like one statement? Like I know that I don't know how to ask my question or if I'm asking it in the correct way.
Well, the idea is that later on today, we're going to derive some formulas that are really not obvious.
So this will help us get there.
Yeah, I will.
Okay.
And the formulas that we're going to derive, they're really important formulas in this course that are definitely part of this course material that's usually covered. And the way that we explain those formulas in Calc B is by using arguments of this form, physicist arguments, I call them.
Okay.
So this isn't rigorous, but the idea is that the volume is approximately given by the sum of these thickened shells, right?
Right.
So then we're just writing down what is the sum of the thickened shells relative to some subdivision and choice of points, right?
Okay, perfect. Thank you.
Good. Oh, and then I'm summing to n minus 1 because I'm starting from 0. Okay, now a physicist looks at this formula and then they just write down then that the volume is the sum becomes an integral from a to b. I have this 2 pi. What is my t sub I? My t sub I is my x. That's my position along the axis, right? F of s sub I is also a position along x. It's just the midpoint between these. Then I have this term. I have, so this outermost delta t sub I becomes dx. Pi times f of x. Now, what does delta t sub I go to as t sub I gets finer and finer? What does the difference between two successive points become? So as the points are getting closer, the distance goes to what?
0.
0. So what happens is that basically here I have a sum. The amount of pieces that I'm taking is getting bigger and bigger, and the pieces are getting smaller and smaller. So the fact that I'm taking more pieces cancels with the fact that the pieces are getting smaller. But here I have a square of the length of the pieces, and it doesn't cancel the second factor. The second factor goes to 0. So this term goes away. And so overall, I just get that the volume is the integral from a to b of 2 pi x f of x dx. And so that justifies the formula for a physicist. And then we ask ourselves, what's the interpretation of this formula? What is the meaning of it? And the meaning of it is that this expression right here, 2 pi x f of x, that's the area of one of these cylindrical shells. And so the results gamma is that I can just integrate the area of the cylindrical shells, and that'll in fact give me the correct volume of the region, right? How do I justify that? Why is this formula true? Well, if I do a physicist justification of writing the area as a sum of thickened cylindrical shells, then using some actual manipulation, like you actually have to do an argument here. This formula is not automatic. And we're going to see that it's not automatic because we're going to see formulas later on that are pretty surprising. They're not what you'd expect. So here a legitimate argument happened. We actually had to have some ideas. We had to factor it. We had to rewrite it. This was a pretty clever thing. But this is the physicist justification for this formula. Last time, I just told you that you could sum up the areas, but this sounds a bit suspicious. Why can you just sum up the areas if they're cylindrical shells? Okay, now we're going to derive the first non-trivial results of the day. We're going to derive a surprising formula. So here we did these two physicist justifications. We justified why the area between two curves is given as integrating the heights of the segments with respect to x. And we justified why the cylindrical shell method works. Then the justification for beta, the fact that you could slice it up into horizontal slices, well, that's basically the same as the justification for A. You just write thickened pieces for alpha. It's not that interesting. So beta is really the same as alpha. But gamma, we had to do some work. Okay, let's do delta, the next thing. So imagine that I have some curve. So let's say this is my x-axis. This is my, this is my y-axis. This is my x-axis. And I have some curve. Let's say this is A, this is B. And it looks like this. Now, let's say I take this interval and I break it up into several pieces. Now, what I'm going to do after breaking it up is I'm going to draw line segments connecting these points. And let's say that my points are t sub I. These are the, this is t0, this is t1, etc., right? So if I look at one of these individual line segments, then what I have is a point here. This point has coordinates, let's say t sub I, and let's say my function is f, and it's f of t sub I. Well, okay, I'm not happy with that because I was going to draw it. Let's draw it below the point. T sub I, comma f of t sub I. And then I have another point right here, and that point is t sub I plus 1, f of t sub I plus 1. And I've drawn a segment between them. What is the length of this segment? So we can do it by Pythagoras, right? What is this measure? What is this length right here in terms of the t sub I?
Is that t sub I plus 1?
Well, t sub I plus 1, but it's t sub I plus 1 is this is a big length. I have to do something with t sub I plus 1. I have to subtract 1.
Minus t sub I?
Yep. Okay, now what about this height? What is this height?
F of t sub I plus 1 minus f of t sub I?
Exactly. And so if I have these two length measures, then what is the length of the diagonal? How can I write the length of the diagonal? Well, come on. Two sides of a right triangle. We know what the sides are. What's the length of the diagonal? Anyone? What theorem do I use? Can someone please answer? How do we get the, what if we know two sides of a triangle, then how do we get the hypotenuse of the triangle?
A squared plus b squared equals c squared.
Right. Well, so if you have a triangle with sides A and B, then what is the hypotenuse? So a squared plus b squared is equal to c squared. Let's call this c. So what does c equal to?
A plus b. Or root a squared plus b
That's
squared.
definitely not how square roots work. You can't
Root.
just, yes,
Root
a squared plus b squared. Okay, so here in concretely, then we can write this as this t sub I plus 1 minus t sub I squared plus f of t sub I plus 1 minus f of t sub I squared, all under the square root. But then I can take this, and in fact, I will take this and move it somewhere else for the same reason as before. Now I didn't have to write it in such a condensed form. I can take this and I can factor out a t sub I plus 1 minus t sub I from the radical. So what I'm going to do is I'm going to write this as the square root of 1 plus. So the person before who suggested taking out a t sub I out of this, that's what we're doing now. So all of this is squared. And then outside of the radical, I get times t sub I plus 1 minus t sub I. And this one, I'm going to rewrite as delta t sub I. So why did we factor it out? Because remember, the delta t sub I becomes a dx. So I want to write this expression as something times delta t sub I. And if I write it as something times delta t sub I, then I get exactly this expression, 1 plus the square of f of t sub I plus 1. Or you know what? I can even write it as I wrote it before. T sub I plus delta t sub I minus f of t sub I divided by delta t sub I squared times delta t sub I. And so this approximate length can be written as the sum from I is equal to 0 to n minus 1 of the square root of 1 plus f of t sub I. I'm a lazy person. Okay, and so then a physicist looks at this and they replace the sum with an integral. They replace the delta t sub I with a dt. And then this becomes the square root of 1 plus what happens when delta t sub I goes to 0? What does this become?
Zero.
Not exactly. This expression right here should remind you of something.
Is it going to be a
Where
trig
have you-
function?
Sorry, go ahead.
I was going to say, is it going to be a trig function? Are we going to try to incorporate that in?
Not exactly. This expression right here, f of, well, okay. Look at this expression. F of x plus h minus f of x divided by h. The limits as h goes to 0 of this is equal to what? We know this. We definitely know this. Anyone at all? This expression right here is, of course, the definition of the derivative, right? Any questions? So remember, you've definitely seen the definition of the derivative before, right? So then what does this become? This becomes a 1 plus what? What do I write here? So this is f prime of x squared dt, right? So what I did is I specifically massaged this expression so that I had this square. This is called a difference quotient. This is a difference quotient, what's inside the limits. Why is it called a difference quotient? Because this is the difference of the f sub I and this is the difference of the t sub I. So it's a quotient of differences, right? And so what we find then is we get a formula for arc length. If we believe that as we make this thing finer and finer, the blue curve, the length of the blue curve approximates the length of the green curve, then we get the formula for arc length. Arc length, which is that L is equal to the integral from a to b of the square root of 1 plus the square of the derivative dx. And so see, and then for physicists, it's obvious why this formula holds. You do this justification, and then a physicist says, okay, I'm convinced. Because as this partition gets finer, the length of the blue curve should approximate the length of the green curve. So here is one of the reasons why I did physicist arguments today, because it lets us derive this formula. And if I didn't do a physicist argument and I just told you that the arc length is this, then why would you believe me? Why is there any reason that this formula should hold? Well, we can interpret it. There is an interpretation, of course. And the interpretation is that if you just look at an infinitesimal segments, well, okay, it's basically the same infinitesimal segment. If you move here distance of dx, then here you move, let's call this delta x. Then here you move f prime of x, delta x. And then if we write this as multiply this by dx through, we get this. Or rather divide through by delta x, then we get this. But once again, the physicist justification should be compelling. We started off with a curve, we split it up into pieces, we calculated the length of the blue curve. It's given by this formula right here. And then it's clear that as delta t sub I goes to 0, well, the sum becomes this, the delta t sub I becomes a dt, and this thing right here, oh, but that looks like the definition of a derivative. And so we get this formula right here. And this is the formula for arc length. And so this is an interesting result, which we've proven like a physicist. So let's do some examples now of calculating arc length. Well, okay, there's one example which is sort of obvious, What's the most important example of arc length? Non-trivial example of arc length. What's a really basic shape whose boundary we want to know? It's a really elementary formula in geometry, right? The circumference of what?
A circle.
Yes. So let's use this formula to find the circumference of a circle. And so this is going to be, again, the first time in your lives. Last time, it was the first time in your lives that you saw an actual derivation of the area of a circle and the volume of a sphere. Now, for the first time in your life, you're going to see the derivation of the circumference of a circle. First, any questions about how I got this formula? The takeaway message, by the way, is that basically you subdivide the interval and then you calculate the length of the blue curve, right? So that should just be the takeaway. If you remember one sentence, it's remember this sentence that we subdivided and we take a polygonal path. It's called a polygonal path. So I can write this as a polygonal path. And then we calculate the length of the polygonal path. And in the limits, it becomes this integral. Just the Pythagorean theorem. That's it. Okay. So we begin with the equation x squared plus y squared is equal to 1. And instead of finding the circumference of the circle, sorry, a equals r squared. We'd like to actually split this into two different pieces. So the circle is notably not a function. This is not a function. But we can write, for example, if we solve for y, y is equal to the square root of r squared minus x squared. But that's not a circle. That's an upper semicircle, right? Which I'm bad at drawing. Circles are hard. So this is given by the equation f of x is equal to the square root of r squared minus x squared. And so let's find the arc length of this curve. We'll find the arc length of this. Of this function f. Of f of x equals the square root of r squared minus x squared from, and then we specify what the parameter range is over. What values are we going to take this over? Well, what's this point right here? What are these points? This is what? It's a circle of radius what? So it's a circle of radius r, right? So the bounds are negative r to r. Okay, let's just calculate what the derivative is. F prime of x. How can someone tell me what the derivative of f is? What rule do I apply?
Chain rule.
Exactly. So the outer function is the square root function. So I get 1/2 square root of r squared minus x squared divided by, and then what do I multiply by?
Would it just be 2r minus 2x, or would you have to?
You're taking the derivative of the inside, right?
Yeah.
So that becomes, it's a derivative with respect to x, right? R squared is just a constant with respect to x.
So, so r squared isn't a variable, it just becomes.
It's just a number. It's a fixed number in this problem. The derivative is happening with respect to x, right?
Is it just
So what's
one?
the, well, what's the inside function? It's r squared minus x squared, right? What's its derivative? The derivative of x would be 1, but it's not x, it's r squared minus x squared.
Would it be minus 2x?
Yep, good. So that's the derivative of the inside. And so we get this expression, and I can just simply write that as x over minus x over the square root of r squared minus x squared. Okay, now let's look at the expression 1 plus f prime of x squared. So if I look at that, that's 1 plus x squared divided by r squared minus x squared. And so that becomes r squared minus x squared plus x squared divided by r squared minus x squared. And then the x's cancel. So then the length is equal to the integral from negative r to r of the square root of 1 plus f prime of x squared dx. And that becomes the integral from negative r to r of, now, so the x's cancel, and I just get the square root of this expression. I get r divided by the square root of r squared minus x squared dx. Does everyone see how I got that?
Do you mind just going through it one more time, please?
Sure. So we took this function f, and we want to know what its derivative is. This is a composition, right? The outside function is a square root function. The inside function is r squared minus x squared. So we differentiated it with chain rule. And then we got this expression. Now, we look at the formula for arc length. Our goal is to calculate the arc length of this curve. So how do we calculate the arc length? Well, there's a formula for that. We just derived it, right? And then we look at the formula, and the formula has this expression on the inside. And I'm anticipating that I'm going to need to know what this expression is. So instead of working with this expression inside of the integral, before I even introduce the integral, I just give you the following 2 mathematical sentences. I make a mathematical sentence that the derivative of f is this. And then I make another mathematical sentence, and that mathematical sentence is that 1 plus the square of the derivative is this. Why am I considering this? Because when I write the formula for arc length, this expression is going to come up. And so how did I do this? Well, I brought it to a common denominator. So I had to multiply top and bottom of 1 by r squared minus x squared. I got r squared minus x squared divided by r squared minus x squared. And then I have a plus x squared divided by r squared minus x squared. And so overall, that just gives me r squared divided by r squared minus x squared, right? I'd cross them out, except for the fact that I really don't want you to cross things out on your homework. I think crossing things out in math looks bad, and I prefer not to cross things out. I would prefer to have a bit more space so that I could write what this is equal to. But anyway, it's pretty clear what happens. And so when I take the square root of this expression, I get the square root of r squared, which is r, and then the square root of the denominator, which is r square root of r squared minus x squared. Is that clear?
Yes, thank you.
Good. Now, what substitution do I make? So I look at this integral. I have r squared minus x squared. What do I let let x be? It's a trig substitution.
Sine of x.
Almost. I have r squared minus x squared. Well, sine of u. So what do I need to multiply sine u by to get rid of this r squared?
One minus.
Well, it's a substitution of the form a squared minus x squared, right? When we have something like this, we substitute x equals what sine u? So we had a table from before, and we substitute a sine u. Why? Because when you write x as a squared sine squared of u, then the a squared, you can factor it out. And then you just get 1 minus sine squared, which you can rewrite as cosine squared. Remember that the main idea behind these trig substitutions is that we want to use Pythagoras to get rid of the square root. And so you make the substitution r sine u. So you were almost right, but you forgot that we needed the r. Any questions about why we make that substitution? So we've seen trig integrals before.
So by substituting just the r instead of the r squared, that like why is it the r and not the r squared? Because of the a squared minus x squared.
Because let's look at what happens when we replace r with x with r sine u. So r squared minus x squared is equal to this, right? Now look at what happens. I distribute the square and I get r squared minus r squared sine squared of u. And so now I can factor out the r squared and I get 1 minus sine squared of u. And 1 minus sine squared is also known as cosine squared. So that's why I substituted r sine u, not r squared sine u, because otherwise I'd have an r to the 4th here, and then I wouldn't have a common factor.
Okay, that makes sense. Thank you.
Right. So in general, when you see x squared, a squared minus x squared, you make the substitution. X equals a sine u. Any other questions? So all of this came up during trig day. It was a pretty intense day in which we did a lot of trig integrals, but this is some trig day review. Okay, what does dx equal? I'm differentiating this expression. Let's say I differentiate this expression with respect to u. What do I get? What's the derivative of sine?
Cosine u.
Yes, r cos u du. I'm unhappy about the fact that everyone started participating a bit less. It's been taking me longer to get responses for the past 2 classes than before. Well, okay, continuing. So, okay, now here is the substantial thing. We're making a substitution. So how do the bounds change? This is what I want to discuss. So if x is equal to r sine u, then what does u equal?
Arc sine u.
Oh, well, it's going to be arc sine something in terms of x. So when I solve for it, what do I get?
Oh, x over r.
Exactly. And so in reality, the substitution that I'm making is this. This is the new variable that I'm introducing. So what do the bounds become? When I plug r into this formula?
Is the lower bound r?
Well, for the lower bound, I'm going to take arc sine x over r, and I'm going to plug in negative r for x. So I'm going to get arc sine negative r divided by r, right? But that's also known as arc sine of -1 to arc sine of 1. Does everyone see why?
Yeah.
Right. And last class, I sent the video lecture a bit late, and I see that a bunch of people didn't come after the midterm. Maybe it wasn't clear whether we would have class or not after the midterm. We have more people today than there were last class. 2 classes ago, we discussed substitution and definite integrals. And last class as well, well, is this what I'm currently on? Let's just go to the file from 2 classes ago. You can see that we did a review of it as well then. When we were calculating the area of a circle. And we did a quick recap that when you have f of g of x, g prime of x, and you make the substitution u equals g of x, the bounds change from a to b to g of a to g of b. And so what we do is we write the new variable that we're introducing as a function of x. Before we wrote the substitution x equals, well, x isn't the new variable being introduced, u is. So we have to solve for it before we apply the function. And that's a thing that you have to remember with trigonometric substitutions. And then, so if you look at last time how we got the area of the circle, it was very similar. We had r to r, we made the substitution r sine u, same substitution as before. And the bounds became arc sine -1 to arc sine of 1. So back to today's lecture. Okay, now what does the body of the integral become? What does the dx become?
R cos u du.
Yep, and then I have an r here, so overall I get r squared cos u du. And then I look at the bottom, and we already wrote out before I erased it what we're doing. So we get minus r squared sine squared of u du. And then by design, this is equal to the integral. Well, first off, let's just say what the bounds are. What is arc sine of 1 equal to? So arc sine is the reflection of the graph of sine in the 45-degree line. And if we look at this point, this is the point 1 comma, and then what is this angle at which sine is 1?
Is it pi over 2?
Exactly. Good job. And then this point is -1 comma minus pi over 2. So arc sine of 1 is pi over 2. And this bound is minus pi over 2. And we did the exact same thing last class when we were calculating the area of a circle. So I can then factor out r from here. Let's do it in multiple steps.
Professor,
Yep.
Should there be 2 DUs above where you're writing? Or
Oh,
one?
thank you. That is a typo. That is, yeah. Good. Thanks. And then we can rewrite this as the integral from minus pi over 2 to pi over 2 of, so the r's cancel. I get a single r, and then I get cos u divided by cos u du. So this is just the integral from minus pi over 2 to pi over 2 of r du. And what's the antiderivative? Oh, well, I can factor, the r is just a constant. I can factor the r out front. So this is the integral of 1 du. What's the integral antiderivative of 1?
R squared over 2?
No, it's not. R is a constant. R isn't the variable of integration. This is the function 1 du, right?
Oh, R.
Well, the variable of integration is u, right?
Oh, then U. Okay.
Yeah. So I evaluate this from minus pi over 2 to pi over 2. And then if I look at the difference between those two, it's just pi. So I get pi r. So pi r, therefore, pi r is the arc length of the semicircle. So circumference is equal to 2 pi r. If we remember what we were doing, we started off with here. We wanted to find the circumference of a circle. So we wrote half of the circle as a function, square root r squared minus x squared. The bottom half would be minus square root r squared minus x squared. But their lengths are equal because one is just a reflection of the other. And I mean, you could do the calculation. You get the same answer if you looked at the bottom half. And so for the top half, we did this integral, we did the substitution, we remembered to change the bounds correctly, and we got pi r. And so the circumference of the circle is 2 pi r. And so this is the first time in your lives that you've seen this formula carefully derived. So we have thus far applied calculus to find the area of a circle, the volume of a sphere, and the circumference of a circle, which is pretty cool. Any questions?
I have a question. It might be a stupid question, but so obviously C is the circumference, and I know that we use C for when we use the constant too. Is there a way to differentiate between the two, or it's just it doesn't matter since we're not using both of them in one equation, in one problem?
Right. So this is a matter of communication. It's not a matter of being absolutely mathematically precise. There's no sort of algorithm for what specific letters mean. You use letters to communicate things to other people. And so in this case, we started off the question by saying that we want to calculate the circumference of a circle, right? So then I used capital C. It's not the constant of integration. The sentence that I wrote at the beginning is reasonable. For example, why do we call the arc length L? Because the English word begins with an L, right? And does that have anything to do with math? No, it doesn't, right?
Okay, that makes sense. Thank you.
So long as it's clear what you're saying, remember that we have a bunch of other notational conflicts. If I write something like 1, 2, that could be two things. It could either be the point or it can be an interval. Which do I mean? It has to be clear from context, right? If it's ever ambiguous, then when you're writing something, then you should disambiguate. You should say the point 1, 2, or the interval. And then most of the time, you don't have to disambiguate because it's clear from context which one it is meant. Okay, let's do 2 more examples of arc length. So admittedly, the examples of just calculating the circumference of a circle, it's one of the harder examples. Ditto for finding the area of the circle, because you have to do these trig substitutions. Let's do a few examples that might appear on the homework. I mean, the homework's out. These are similar to examples that appear on the homework. So let's, for example, take f of x equals 1/3 x squared plus 2 to the power of 3/2 over the interval 0 to 1. So the question is, find the arc length of. So as before, we know that the formula for arc length involves this expression 1 plus f prime squared, right? So a good way to start would be to calculate what f prime is. What rule am I applying?
Chain rule.
Yep. So this is the outer function is x to the power of 3/2. The power comes down, and if I multiply 3/2 by 1/3, I get 1/2. Then I write x squared plus 2 to the power of 3/2 minus 1 is 1/2, and then I need to multiply by something. What's the derivative of the inside?
2x.
Good. So I can just rewrite that as x times the square root of x squared plus 1. That's the derivative. Okay, now let's consider the quantity 1 plus f prime of x squared. So I get 1 plus x squared times x squared plus 1, right? 1 second. Okay, sorry, it's x squared plus 2, not x squared plus 1. That's the problem. Whoops. There we are, much better. Okay, so if I expand this, that's equal to x to the 4th plus 2x squared plus 1. And how can I rewrite this as? What can I rewrite this as?
Is that x squared plus 1 squared times x1
Exactly.
plus 1 squared?
Oh, well, it's the square. Yeah, but you're right. Exactly. So why do you recognize this? Because if you look at x squared plus 2x plus 1, you know how to factor this. This is ingrained in your memory. We factor this very frequently. And so here it's just we replace x with x squared and we get this. But okay, why is this good? Because we want to take the square root of this expression, right? And so we're taking the square root of a perfect square. So the length is equal to the integral from 0 to 1 of the integral of 1 plus f prime of x squared dx. And that's the integral from 0 to 1 of the square root of this expression. So that's x squared plus 1 dx. And what's the antiderivative of the thing on the inside?
X to the 3 x cubed over 3 plus x.
Exactly. Good. And so we take this and we evaluate it between the bounds 0 and 1. And so at 1, I get 1/3 plus 1. And here, well, both just have x, so it's 0. So I can write that as 4/3. Arc length found. Okay, that's one example. Let's do another example. It's similar. Let's separate it off like this. Find the arc length of. Usually I'm the more student. Now let's consider the function f of x is the logarithm of cosine of x. Over. Now I specify the bounds over which we're integrating. 0 to pi over 6. Okay, so we look at the problem. The problem asks us to find an arc length. So we know that the expression 1 plus the derivative of f squared, so this the square of the derivative, is going to be important. So a great place to start would be to calculate what the derivative is. And what is the derivative? What rule am I applying?
Chain rule?
Exactly. And so what do I get? What's the outer function is log. What's the derivative of log?
One over cosine x.
Yeah, so the derivative of log is 1 over x, and then I plug in the inside function, so I get 1 over cosine of x, exactly. And now I need to multiply by the derivative of the inside function. What is the derivative of the inside function?
Negative sine x.
Exactly. So I can write that as minus tan x. So this function is chosen to be nice. Well, now you can see what's going to happen when we consider this expression. So I get 1 plus tan squared x. What is that equal to?
Secant squared x.
Good. By the second version of Pythagoras, which you should have ingrained in your memory almost as well as the first version of Pythagoras. It comes up a lot. So then when we consider the arc length, that's the integral from 0 to pi over 6 of the square root oh no. Oh no. Okay, it's not as nice as I expected. I made a mistake in my notes where I forgot to take the square root. Okay, this example is less elegant than I would have hoped. So that becomes the integral from 0 to pi over 6 of secant x. And this integral I did before. It turns out that the antiderivative is the logarithm of secant plus tan x. And then we evaluate that from 0 to pi over 6. And then this is because we did this integral before. And I would have hoped not to quote the results, but I made a mistake in my notes. In my notes, I forgot to take the square root, and then I just said, oh, the integral of secant squared, it's tan. And no, but we have to do the integral of secant, and then you get this expression. This before. Sorry that I have to quote. Okay, but anyway, let's quickly remind ourselves what the values of the trigonometric functions are. So first off, what is pi over 6? Pi over 6 is, well, pi is 180. 180 divided by 6 is 30. So this is the 30, 60, 90 triangle. The bounds in almost all definite integrals, which in any way involve trig functions, the bounds are not chosen arbitrarily. The bounds are chosen to be nice. So pi over 6. What is cosine of pi over 6?
Radical 3/2.
Good. Oops. And what is sine of pi over 6?
One half.
Okay. So this, thanks. This is equal to cosine pi over 6. And this is equal to sine of pi over 6. And I'm happy to do this example because in the homework, I'm putting a bunch of definite integrals. Well, there are definite integrals. And you need to remember your two special triangles. They come up a lot. Okay, so what is secant? Secant is 1 over cosine, right? So then if I plug this in, I get logarithm of the absolute value of 1 over cosine of pi over 6. So that's 2 over root 3. And then I get tan. Tan is sine divided by cosine. So when I take 1/2 divided by 3/2, I get 1 over root 3. And then I get minus logarithm. Well, now I look at 0. Tan of 0 is 0. And cosine of 0 is equal to what?
1.
Right. So secant of 0 is also equal to 1 because it's 1 over cos plus 0. So I just get log 1. What does log 1 equal to?
0.
Yeah. So then I can rewrite this as log of 3 over root 3 minus 0, which is the same as log. And then I can remove the absolute value bars. It's a positive number. Log of root 3. So fun fact, the arc length of this function from 0 to pi over 6 is log of root 3, in case you were wondering. Okay, now here is where I reveal there is a bit of sleight of hand going on. And so let's say I have a circle of radius r. Then I get that the circumference of the circle is equal to 2 pi r. Okay, now let's say I scale this by a factor of 2 in one axis. And this is happening in the y-axis. And so I get an ellipse. And the axes of this ellipse are r and 2r. And so what would you think the circumference of this ellipse is? If I multiplied everything here by 2 and it's a length, then how should it scale? This is just a guess.
2 pi 2r, wait, 4 pi r
Yeah.
squared.
Well, not r squared, it's the circumference. But so you'd guess 4 pi r, right? Because you've just multiplied everything by 2. So it turns out that this does not equal. And in fact, there is no elementary relationship whatsoever between these two lengths. So there is actually no formula for the circumference of an ellipse. You can write it as an integral, that counts as a formula, but you can't write it in terms of calc A functions. For the circumference of an ellipse. Is ellipse spelled with 2 L's or 1 L? I think maybe it's 2. Now, why is it very clear that there's no such formula? Because look at what happens when we calculated the circumference of a circle. We looked at this expression, we squared it, and then when we summed 1 plus this, we got an r here, right? Now let's imagine that we multiply the derivative by 2. So if there were a 4 here, then we'd no longer get that the x squareds cancel. Because now we would have x squared plus 4x squared. And so the numerator would no longer be nice. Similarly, look at all of these examples. In these examples, we had perfect squares. If you multiply this by 2, then that no longer becomes a perfect square. Ditto here. This factorization, it relies on this. So if you just scale a function by 2, the integral that you're solving might become absolutely terrible. In fact, all of the integrals that you've been solving in this course have been specifically chosen to be integrals that can be solved. If you just change one of the numbers by a little bit, it can happen that the integral becomes no longer solvable. So in general, if you just write down an arbitrary function, if you just take these functions and you multiply them by 2, then you're no longer able to calculate the circumference of an ellipse, of those curves. The fact that those integrals are solvable is happening because the numbers have been very cleverly manipulated in order to get the integral to be nice. Because you have this expression 1 plus the square root of 1 plus something squared. We're really relying on the fact that we have some way to deal with the square root when we're integrating this. And since we're adding 1 plus something, scaling this doesn't scale the expression inside the square root. It only scales one of the summands. And so the integral can quickly become terrible. And all of the integrals that we've done, if you take the function, you multiply it by 2, you can no longer calculate the arc length. The integrals become unsolvable. So I am giving you the false impression that you can now calculate the arc length of every single curve. We calculated the arc length of a circle, hurrah, hurrah, but we can't calculate the arc length of an ellipse. Can't be done. There's no formula in terms of calc A functions. So yes, I should reveal this fact that all of the examples of arc length are chosen very carefully. And if there's a factor of 1/2, that factor of 1/2 is important. Because if the factor goes away, the integral becomes insolvable. So yeah, I'm giving you a false impression that you can actually calculate a bunch of arc lengths right now and get nice numbers. Most of the time, there are no nice expressions. Okay, so I think it's time for a break. We finished this section on arc length. Up next is polar coordinates. Let's see, what time is it? It's 42. So let's take a 13-minute break, and then maybe I can take another break for 42, 45, 55. So break until 7:55, right? Unless someone has some questions first. Does anyone have any questions about what we've done? By the way, I keep getting surprised by this fact. I knew this fact before, that there's no formula for the ellipse. And then when I was preparing this lecture last night, I looked at the formula for arc length and I realized that all of these examples, if you just multiply it by 2, nothing works. So I rediscovered this fact, and he keeps surprising you over and over again. That's scaling the circle, bam, no nice formula. Gone. No elementary relationship. It's sort of disturbing. Anyway, break until 7:55. See you then. Okay, let's resume. So the next topic is going to be an extended section about polar coordinates. And these are going to be on the next homework. So for the current homework that I put out today, it ends on arc length. And then, I mean, there's a question after the arc length questions, which is an integration question, but you know how to integrate already. The last material covered is arc length. So this is reserved for the next assignment. Now, what are polar coordinates? Well, given a pair r comma theta, we can consider the following thing. So let's say this is our Cartesian plane. We take a ray at angle theta away from the positive x-axis. All angles are measured with respect to the positive x-axis. And then we go a distance r along this ray. And that defines a point. We can consider taking the ray at angle theta. And this is, of course, to the positive x-axis. And moving our units along it. From the origin. And so this scheme is a different way of referring to points in the plane. This scheme is a different coordinate system. For referring to points in the plane. Now, what are some things about this coordinate system? Well, first off, what is the point that I'm describing? So if I have in polar coordinates, these are called polar coordinates. If I have in polar coordinates the point r comma theta, then how do I convert this into Cartesian coordinates? Which is our usual system. So let's look at the diagram. I'm going to draw it again. If we have a angle theta and a distance r along this, then if we look at the x and y coordinates, they're these sides of the triangle. And we can find those sides using trigonometry. So what is the height of this triangle? If the hypotenuse is r and this angle is theta, then what is this side? Anyone? Okay, what if we have side length 1, angle theta? What is this side? This is a right triangle. What is this side? I really rely on participation, so can people please answer?
Tan.
Well, tan is the ratio of these two sides. But the height, it's not tan, it's
Sine.
yes, sine theta. And this is cosine theta. So if my hypotenuse is length r, then what is the height?
Sine.
Well, I've scaled everything by r now, right? It's not 1, it's now r. So what do I get?
R sign?
Yeah, exactly. Thanks. And this is r cos theta. And if you look at, for example, the ratio of this side to this side, then it's r sine theta divided by r, so that's sine theta. So indeed, the sine of this triangle is sine theta. So that gives us a way for going from polar coordinates to Cartesian coordinates. The x coordinate is r cos theta, and the y coordinate is r sine theta. So to give some examples, let's suppose where's my first page? This is my first page. Okay. Oh, right. I'm first here, and then I go here. So suppose I have, for example, let's do polar coordinates to Cartesian of the point, and then so this is going to be a point in polar coordinates, 2 comma 5 pi over 6. Sorry, yes, 5 pi over 6, which I'll write as 5, 6. My 5 looks like a 6, perhaps. Now, let's look at this geometrically. If this is my unit circle, and I look at an angle that's 5 pi over 6. Then what is this angle right here?
Pi over 6?
Exactly. And so then if I look at, for example, the cosine of 5 pi over 6, it's going to be negative, right? Because if I look at these projections, then this negative length right here is going to be the cosine. But we can also write that as minus the cosine of what angle instead? So looking at this diagram,
pi over 6?
And the reason that I'm doing this is because we're not familiar with the angle 5 pi over 6. But if we look at it geometrically, then we can see that it's just negative the cosine of pi over 6. The cosine of pi over 6 is this length and it's positive. But if I look at the cosine of 5 pi over 6, it's this length and it's negative, right? Because it's negative. It's this coordinates. But cosine of pi over 6, I know, because if I look at pi over 6, that's 30 degrees, right? So if I remember my triangles, and the reason that I'm doing this to oblivion today is because on your homework, you have a bunch of definite integrals, and those definite integrals involve numbers, like actual numbers. Calculus students always say that they want examples with numbers. Well, there you go. You have a homework with a bunch of examples of numbers. But in this case, in order to get those numbers, you need to remember your two standard trig triangles. So if we have pi over 6, right? Then what is the cosine of pi over 6?
Radical of 3 over 2.
Good. So cosine of 5 pi over 6 is minus root 3 over 2. And what about the sine of 5 pi over 6? Well, if we look at the picture, then the sine of 5 pi over 6 is this height, right? But it's the same as though we were taking the sine of pi over 6. Because if we just look at the picture, then both of them represent this height, right? And so what is this side?
1/2.
Exactly. Okay, so r cos theta, comma r sine theta becomes, now if I look at what my radius is, it's 2. And so what I get is that the coordinates are twice this, which is minus root 3, and then twice this, which is 1. So this point, if I look at taking it twice the that of the unit circle, then I get exactly these coordinates. So this is an example of converting from polar coordinates to Cartesian coordinates.
I'm sorry, where'd the 2 go again?
The radius, what's the radius of the circle that we're looking at?
Oh, got it. Okay.
Yeah, so r is 2, and we found r cos theta and r sine theta. So it becomes this. Now, why don't we use polar coordinates all of the time? There are a few problems with polar coordinates. Well, problems with polar coordinates. Well, first off, suppose you take any angle and then you set the radius equal to 0. 0 comma theta always denotes what? Which point? If I set the radius equal to 0, then which point am I referring to? So if I set r equals to 0 in this formula, then what do I get?
0, comma 0.
Yeah, and that's also known as the origin. So the representation is not unique. But also, at the same time, suppose that we change the angle and we add 2 pi to it. R comma theta and R comma theta plus 2 pi. So if you go around the circle and you wrap around, what ray do you get? Is it the same ray?
Yes.
Yeah, so the thing is, these two things, they denote the same point. And that's not it. We have one more degeneracy. If R is less than 0, then we go in the opposite direction. So for example, if I consider something like, let's say my angle, the point, let's say my radius is -1 and my angle is pi over 4. So if I look at the ray at angle pi over 4, it's this ray right here. But then if I go -1 units along that ray, I get this point. Now, what's another way of referring to that point? Without, with a positive radius.
Can you just subtract pi from pi over 4?
Yeah. Yeah, so if there are 2 pi radians in a circle, so if I add or subtract pi, then I get around. So also, this is 1 comma pi over 4 minus pi, because that's the opposite ray, or 1 comma pi over 4 plus pi. So in general, I'm going to write it like this. R comma theta and -r comma theta plus pi denote the same point as well. So one deficiency with polar coordinates is that the representations of points are far from unique. Far. Oops. And I can highlight this in blue. So we see 3 degeneracies already in these examples. But nonetheless, it turns out that working with polar coordinates in a lot of examples is very nice. Let's before say how we go from Cartesian to polar. By the way, are there any questions about this? So I've introduced a new idea, and that's what happens if the radius is negative. Then we just go in the opposite direction. Now, if I just give you a pair, you can ask yourself, how do I know if it's in polar coordinates or Cartesian coordinates? Well, you have to say explicitly. I mean, by default, it's in Cartesian coordinates, but if we're working in if polar coordinates sometimes come into the picture, then we have to be explicit about which we mean.
When you say go in the opposite direction, can you just explain that one more time?
Right. So here, let's look at the ray at angle pi over 4. So let's consider the point 1 comma pi over 4. So the angle is pi over 4, and I go a distance of 1 along this ray, right? So I get this point. Does that make sense? Now, what happens if instead I consider -1? I'll write this in red and draw it in red. Comma pi over 4. Then what happens is instead of going along this ray, I go along the opposite ray. And I get this point. Is it clear now?
Yeah.
Right. Thanks for asking. So this is what happens. Before, I didn't suggest that negative radii were possible, but now I'm saying that they are, and this is how we read a negative radius. We look at the antipodal points. And then there's a degeneracy where it's the same as going negative that many units in the opposite direction. And the opposite direction is given by theta plus pi from theta. Okay, let's consider Cartesian to polar coordinates. So suppose that the way that I wrote it before was I wrote it in green, polar coordinates, Cartesian coordinates. So now suppose that we have Cartesian coordinates, and we care about the polar representation. So your Cartesian coordinates are typically written as x comma y, while your polar coordinates are typically written as r comma theta. That's one way to tell the difference if they're written using variables. And I wrote this in blue before. I should match my color scheme. And then the question is, how can I fill these out? So first off, what is the radius? So let's draw a picture. So if I move x units along here and y units along here, then how far have I moved from the origin? Well, what theorem do I use?
Pythagorean theorem.
Exactly. So I get what?
Root x squared plus y squared.
Thanks. Okay, good. So remember that the representation of the radius isn't unique. We could also represent it as a point with minus r. But the distance is square root x squared plus y squared. Now, what's if this angle is theta? Then what does tan theta equal? Which ratio is it in this triangle?
Y over x.
Exactly. Consider the quantity arctan y over x. So this is not defined when x is equal to 0. And Otherwise, the range of this function is what? What values does arctan span between? So the graph of tangent looks like this, right? And the graph of arctan looks like a reflection of this graph.
Is it 1 and -1?
Well, so the height here is going to be the same as the place where the asymptote occurs, right? And where does the asymptote occur in tangent? When does tangent blow up?
Is it pi over 2?
Exactly. So if you look at the range of arctan, it's minus pi over 2 to pi over 2. Is well, I can write it as an interval, minus pi over 2 to pi over 2. So in general, if I consider this quantity, I'm going to get an angle between here. So if I look at this range, I'll get an angle in here. I'll get some of these rays. Not including the vertical rays, because x equals 0 fails. Now, okay, then if my x coordinates is greater than 0, then what can I say about the angle if I just naively look at the angle? Will an angle in this range work?
Yes.
Yeah. So if x is greater than 0, then an angle in this range works. And then I can say that if x is greater than 0, so the coordinates x comma y become, what's my radius? What did we say the radius was?
Is that the root x squared plus y squared?
Exactly. And then we said that an angle that is within the range, so the tan of this angle will exactly be y over x, and then this denotes a unique angle, and that's the angle that we want. So we can consider arctan y over x. And so this is, if x is greater than 0, this is how we convert from Cartesian to polar. Now, what happens if x is less than 0? And remember, these representations aren't unique. I could consider some other ones as well. Then instead, so the problem with the angle is that let's see, which two angles are tan equals? If I have this ray right here, and I have this ray right here, then the tangents of this ray is the ratio of these two sides, right? And the tangent right here is the ratio of these two sides. But if I look at what happens, both of these sides change by a sign, right? So in general, tan, or you can say it like this, tan is periodic with period pi, right? So tan theta is equal to tan theta plus pi. So when I can consider the angle arctan y over x, if x is less than 0, then I'm actually getting the antipodal angle from the angle that I want. Now, how can I correct that? I can either add to the angle or I can make the radius what? So I can make the radius negative. And then consider arctan y over x. There are different formulas for this. Again, the representations aren't unique. I could say, or instead, I could make the radius positive and I could add to the angle. If you don't like negative radii, then you can say arctan y over x plus pi, right? And if x is equal to 0, then I guess I can write 0, comma y. What's one way to represent 0, comma y? So what should my radius be?
Zero?
Well, that represents the origin. I don't want the origin. I want the point 0, comma y. How far away is y from 0? Well, the distance is y, and this can be a negative number, and I can take the angle pi over 2. That's the vertical line. So that means go y units along this ray, and then I get to y, right? I mean, or I could do an absolute value of distance. But then I'd have to do casework. Then it would either be pi over 2 or negative pi over 2. This is the simplest way to write it. So the problem is that because of this non-uniqueness of representation, we sort of have cases. This isn't as elegant as one would hope. But we do have some things. We can say what the cosine of, let's say we have coordinates x comma y. Then what is cosine of theta equal to? So to remind you, here we have x, here we have y, here we have radical x squared plus y squared. What is cosine of theta?
Is that x?
Divided by what?
Divided by
Because
y?
it's not, that would give you cotan.
Oh, divided by root x squared plus y squared.
Yes. Similarly, what is sine of theta?
Y over the root x squared.
Exactly. And then we already discussed tan theta, but the thing with tan theta is that it's not always defined. It's only defined when x does not equal to 0. But these things, these are always defined. And so in general, if you consider a triangle, these define, and the values define a unique angle modulo 2 pi. So we can never tell the angle up to an additive factor of 2 pi, a suband of 2 pi. It's not a factor exactly. But just knowing sine and cosine, and these formulas are always make sense. These are always defined except at the origin. Of course. So this, the going in this direction isn't always as nice as you would hope, but at least you have this, and this is going to come up in problems. So let's do an example. Let's do Cartesian to polar. Of the -1 comma √3. So if I'm going to plot this point, it's easy to plot Cartesian coordinates. -1, and then √3 is about 1.71. Okay, what can I set r equal to? So what is this length? How can I write the length?
Can I ask a quick question before?
Go ahead.
I'm sorry. Will these pictures or things that like for these specific questions, these are the ones that we have to draw ourselves, right? It's not going to be like with the problem.
It's not.
Okay.
Yeah, a great way to start the problem is to start by drawing a picture.
Mhm.
Right now, we're just plotting points. As soon we're going to start plotting graphs.
Okay.
And I'm going to teach you how to plot graphs. Okay.
Would it be,
go ahead.
would it be like, are we doing it in the same form that we've been doing the other ones, like the square root x squared plus y squared?
Yes. So we take -1, we square it, and we take √3 and square it. And what do we get?
1 and 3.
And what is the square root of 1 plus 3?
2.
Yep. Okay. Now, what about this angle? Let's say we're aiming for this angle. Now, the problem with arctan is that it's not going to give us an angle in this range. We have that x is less than 0, right? So let's use this formula. Let's use arctan y over x plus pi. Because the radius is positive, and if we want the positive radius, then we have to use this formula. So arctan of y over x, √3 over -1, plus pi, which is arctan of √3 plus pi. And of course, again, on your homework, you're going to encounter expressions like this. And part of why I'm doing this is because on the homework, again, definite integrals, you'll have these as bounds. Let's draw the triangle. So if we consider a triangle in which sine is √3 times bigger than cosine, Well, we know such a triangle. If I have root 3 over 2 and 1/2, then the ratio of sine over cosine is equal to root 3, right? Sorry, this is arctan negative root 3. I forgot the negative sign. Okay, what angle do we have here if it's root 3 and 1/2? Then what angle is this?
Pi over 3?
Yep. Pi over 3 is 60 degrees because 3 times 60 is 180, which is pi. Sorry, I wrote pi over 6. I meant pi over 3. But now let's look at what happens when we consider in our range. Our range is here to here. So if instead we make this negative root 3 over 2, then what angle do I get here instead? If I'm measuring it from the positive x-axis.
Just negative pi over 3?
Yeah. So then if I look at this angle right here, it's minus pi over 3. That's what arctan of negative root 3 is, because arctan always gives an angle in the range. We discussed this before, negative pi over 2 to pi over 2. And this is the unique triangle angle, which gives you that value of tan in this range, plus pi,
Quick
which
question.
we can write. Yeah.
Just going back to the original triangle, like where, how do you know it's pi over 3 again? Just making that.
Oh, so
connection.
it's the number root 3. So there are only 2 special triangles, right? Now you think about arctan root 3. In which special triangle is the ratio of the opposite side to the adjacent side equal to root 3? Because what is tangents? Tangent is the ratio of these 2 sides, right? Do you agree?
Yeah.
So there are 2 special triangles. The other triangle, these 2 sides are equal, so the ratio is 1, right? So what is arctan? What is arctan of 1? What's the angle at which sine and cosine equal?
Pi over 4.
Yeah. Now, what about arctan root 3? Arctan root 3 is the angle at which this ratio is root 3, right? And what angle is that?
Pi over 3.
Yeah. And then arctan negative root 3 is minus pi over 3. So once again, these are very special numbers. Oh, what about arctan 1 over root 3? What's that equal to?
Is that pi over 6?
Exactly. So if it were 30 degrees instead of 60 degrees, then you'd swap these 2 sides. So these are your special values of arctan. On the homework, you'll, for example, need to know what the value of arcsine of 1/2 is, and you can compute that using special triangles. But anyway, these are your special values of arctan. So again, this point was chosen so that it would work. So you get polar coordinates. So 1, 3, negative 1 root 3 becomes, if this is in cart, then in polar. And once again, the representation isn't unique. We discussed this. The radius is 2, and the angle is 2 pi over 3. So that's another example. So here are 2 examples of converting both ways. And in this example, we had x is less than 0, so we had to remember to add pi. So this is another coordinate system. Go ahead.
Just back to the special triangles thing. I'm just having a hiccup with that. So like for the arctan, we were using, like, are we using the same triangle for like the arcsine as well?
Well, there are two special triangles, right?
Yeah.
Now, what changes between arcsine and arctan is what ratio you're considering, right?
Yeah.
Because in sine, you just care about the ratio of one side to the hypotenuse, but the hypotenuse is 1 in the special triangles, right? So you're just
Right.
looking at a side. So I'll give you a homework spoiler. What is arcsine of 1/2? This comes up in the homework. What triangle has a side length of 1/2 along its sine? So if this side length is 1/2, that's the sine, right? Then what is this angle equal to?
Is it pi over 3?
Let's see, pi over 3 is 60 degrees. The cosine is 1/2 in pi over 3. It's not pi over 3, it's pi over.
So pi over 6?
Yeah. So when you have 30 degrees, this side is smaller, it's 1/2. And when you have 60 degrees, it's √3/2. √3/2 is bigger than 1/2, right? So if you just visualize, I guess I'm doing it backwards. This is 30 degrees. So this side is 1/2. This is 60 degrees. Now it's √3/2. Do you see my hands?
Yeah.
Right. So arcsine of 1/2 is equal to pi over 6. And that's going to come up in the homework.
So just for a method of doing that, could we also just like have visualized the unit circle in our head?
Yeah, you can visualize. So all of these unit triangles are part of the unit circle, right? So I could draw the axes and I could draw the circle. So that works just as well.
Okay, thank you.
Trig isn't about triangles, it's about circles, really, right? What are sine and cosine? They're defined in terms of lengths along the unit circle. Let's see, how much time do I have? Okay, so I'm not going to get very far today. We're going to do most of polar coordinates tomorrow. Let's discuss graphing in polar coordinates. So typically when we're working in Cartesian coordinates, a function looks like typically is y equals f of x. Y is some function of x, right? We're used to this. So in polar coordinates, we write what is going to be, so either r is going to be a function of theta or theta is going to be a function of r. Which one do you think it is? So are we going to give the radius as a function of theta or theta as a function of the radius?
Theta is a function of the radius?
Well, what would that look like? That would mean that at each radius, we have a theta. That would mean that at every single radius, we'd have to have some angle. So for example, that would mean that I would need my curve to go to infinity in some sense. It would have to start at 0 and it would have to go to infinity. But I want graphs that are nice and compact. it's much more natural the other way around. We write r as a function of theta. And what does that look like? Then as you go around the circle, you're saying what the radius is. So this says the radius at a given angle. So I'll give an example. Let's consider the equation r equals 1. And then typically, we were going to restrict it to some range of values. For theta, that's the function. Let's say for theta ranging from 0, and then let's say 3 pi over 2, which is going to be negative 90 degrees. What does the graph in polar coordinates look like? So for example, at theta equals 0, I have r is equal to 1, right? So I plot the point 0, 1. Now, at radius pi over 2, what is r equal to? Does it change?
It's the same, right?
Yeah, so it's always 1. And so at this angle, it's 1. At this angle, it's 1. And what do the angles range over? The angles range from 0 to 3 pi over 2, right? So that represents this range of angles. This angle is 3 pi over 2. And so what do I get in that range of angles? It looks like part of a what? So if the radius is always the same, then what do I get?
One.
Well, that's what the radius always is. What does the shape look like when I plot it in polar coordinates?
Circle.
Yeah. So I exactly get a circle, except for the fact that I've restricted my theta to lie in a certain range. So I get 3/4 of a circle, right? So this restriction means that I stop here. The range I'm plotting over the given range. And so the equation r is equal to a constant gives a circle. In polar coordinates, we'd have to write x squared plus y squared equals r squared. In Cartesian coordinates. But in polar coordinates, it's a much simpler equation, right? Okay, let's consider the example r equals theta. And let's consider this for 0 is less than or equal to pi is less than or equal to 4 pi. So we're going to go around the circle twice. So when r is equal to 0, when theta is equal to 0, r is equal to what? Let's draw a table. Theta, r, right? Theta is equal to 0, r is equal to?
1.
Well, look, what's the equation?
Oh, 0.
Yeah, at pi over 2, I get,
Pi over 2.
yeah, it's just the identity function. And so if I continue this at pi, I get pi, and then at 2 pi, I get 2 pi. And at 4 pi, I get 4 pi. So I start off at the angle 0. Then let's say that this is going to be 4 pi. And let's say that this is 2 pi. And then let's say that this is, if this is 2 pi, then this should be pi. This should be pi over 2. This should be this. And if I plot it, and then let's see if this is this, and then I also add this, I should get this here. Okay, I completely erased that. I did not intend to completely erase it. And how would you describe that shape?
Spiral.
Yeah. So this is a poorly drawn spiral. Well, mathematically, it's a spiral, but in our case, it's poorly drawn. Okay, so that's another equation that you can get. And then because of the range of angles, it goes around twice. So notice how we get each ray has, well, for 0, it has 3 points over it. For all the other ones, it has 2 points over it. So this is how you can draw, this is how polar coordinates work for functions. You give r as a function of theta. Now, there's one thing that I want to mention about polar coordinates. If f of alpha is equal to 0, but f of theta does not equal to 0 near alpha, then the curve f of, r equals f of theta is tangent to the ray. Well, let's say to the line. Theta equals alpha at the origin. So for example, if you look at the spiral, look at how the spiral comes in. It's tangent to the line theta equals 0. So this line right here, it's theta equals 0, right? And notice how this is tangent to how I've drawn it. I'm going to give some more examples, but do you see what feature of the graph I'm describing? The fact that it comes in tangent to the line theta equals 0.
Could you point it out one more time?
Right. So let's zoom in. If I look at what happens at 0, let's say this is pi over 2. Then if I look at, for example, the angle 1/2, at 1/2, it would be pi over 4. If I look at half of that angle, it would be half of this measure right here. And then if I actually complete these things into a curve, let's draw some more points. Now, so let's shade those points in. At half of the angle, it's half of this. Then at half of that angle, it's half of this. And then it's 2 3/4 of this. And if I sort of complete that to a curve, what I discover is that this curve comes in and it's tangents to this line. So notice how it doesn't come in at any other angle. It comes in at the angle 0. Do you see what I mean now?
Wait, so the dots, can you explain where you put the dots again?
Right. So at the angle theta, the distance that I'm going is theta, right? So here, let's say this is pi over 2, right? Let's draw the circle of radius pi over 2. Whoops, that disappeared for some reason. Okay, this is my attempt to draw a circle, quarter circle of radius pi over 2. It's a bad attempt. So this is half of the angle, right? This is half of this angle. So this point should be halfway along this line. This is a quarter of this angle. So it should be quarter way along this line, right?
Oh, yeah, okay.
So I can actually plot, like in high school, how did we plot functions? Let me open the curtain so I have some more light. In high school, we would draw a bunch of points and then we connect them with a line. So I've done that here. I mean, I haven't drawn enough small ones, but this line comes in at an angle of 0. Perhaps if I did stroke eraser. If I draw it like, whoops, this, it will be clearer. So if f of alpha is equal to 0, but f of theta is not 0 near alpha. So if it's not always 0, if it's just 0 for at this point, then we have a tangent to the line of at angle alpha. In this case, f of 0 is 0, so there's a tangent to the line at angle 0. So do you see this feature? This is a very prominent feature of this graph. It curves in all the way around, right? So I'm just going to quote this for drawing polar functions. Let's consider the function r equals sine of 2 theta. Let's do a plot, by the way. Well, so first off, let's just consider a Cartesian plot of sine of 2 theta. So sine of 0 is 0. And then let's just draw a regular sine wave. Now, if we consider sine of 2 theta, then all of these things happen earlier. So this would usually happen at pi over 2, but now it's happening at pi over 4, right? This is happening at pi over 8. This is happening not at pi, but at pi over 2. Sorry, this would no. Bad. This would usually happen at 2 pi. Sorry, this is a full period. So this would usually happen at 2 pi, but now it's happening at pi instead. This would usually happen at pi. So this is happening at pi over 2. This is happening at pi over 4. So it reaches its maximum at pi over 4, and then it's 0 at pi over 2. So let's draw this plot now. So it's 0 at at 0, and it's 0 at pi over 2, right? So let's plot this for theta. For 0 is less than or equal to theta is less than or equal to pi over 2. Now notice that it's 0 at 0 and pi over 2, so it has 2 tangents here. It reaches its maximum at an angle of pi over 4. So let's say this is the maximum value right here. And then I'm going to draw the curve in blue. And so if I were going to complete this, it would look something like this. It starts off 0 here, its tangents to it. Then it reaches its maximum value. And then this side is symmetric. So this is an approximation of what this plot looks like in this range. So does everyone see how the radius is biggest at angle pi over 4? Any questions about this plot? Does everyone see how I got this? Oh, okay. Now let's consider this. What if what's if I continue to plot it? Over 0 is less than or equal to theta is less than or equal to 2 pi. So if I imagine the angle theta increasing, then I start here. So watch me draw the curve in real time. This is theta equals 0. This is theta equals pi over 2. Then it comes in. And it closes in here. So it's not perfectly symmetric, but it approximately looks like that. Okay, what happens now? Now my angle is this. And then my angles start becoming this, right? But what is my radius? My radius is now negative. So where does this curve continue drawing itself? Let's draw an arrow. This is how I'm drawing it. So this is step 1. Step 1, I go around here. Then how does it continue? The radius is now negative, so I'm looking at the reflection of these rays. And so it goes around here. And now as this ray moves from here to here, this ray moves from here to here. So now I'm drawing this bottom part of the curve. And it's traversed like this. So it's traversed in this direction. So that's my second part of the curve. Now I reach pi, now it becomes positive again. So now I'm traversing this part of the curve because it's these angles and the radius is positive. So now it comes in and now I'm traversing this part of the curve. If I could draw it well. And it's going around in this direction. So that's the third step. And then it reaches here and now the radius is negative and now traverses the fourth step. So now that it's come in through here, it now goes through here. And comes back inside. And now it's traversing this in this direction. So that's the fourth step. And so that looks like the command key on a Mac keyboard. But look at how it's being traversed. It's first going around here, then around here, then around here, then around here. Does everyone see the pattern? you can watch it as an animation. You can imagine the animation of it swooping around. So first around here, then around here, then around here, then around here. So these are what graphs in polar coordinates look like. When we give r as a function of theta. And again, look at the easy examples. A circle, it's great. A spiral, it's great. Super easy to give equations for these in polar coordinates. Mac keyboard figure, it's also pretty easy to give. In Cartesian coordinates, it will be a much worse function. Let's now discuss changing equations between coordinates. So let's first discuss Cartesian to polar. Cartesian to polar. And I'm going to do this through a series of examples. Okay, I think that by now it should be somewhat intuitive as to how these plots work. Remember that I'm just giving the angle, the radius at an angle of theta, and then the angle is, I guess I should do it like this because it's being mirrored, swooping out the circle. And then as the angle swoops out the circle, you can imagine the radius being given by some function on it. So let's say the radius is increasing linearly, then I get a spiral, right? And I mentioned this fact that if the radius is ever 0 and it's not constantly 0, then you get an asymptote at that angle, which it has a 0. So if you look at this curve, then you have tangents at these lines. It comes in at exactly angle 0 and at angle pi over 2. So you can see this as part of the features on this graph as well. I guess I can show you one more thing. I'm going to quickly screen share. So this is what you're not allowed to do when doing homework. You are not allowed to use this to solve things. This is a website that can sort of solve all of your problems, but you're not allowed to use it for homework. But you are allowed to use it to plot things just to get some intuition. So let's look at the equation that we had before. It was r equals sine of 2 theta. And so it'll give me this polar plot. Look at this. That's what the polar plot looks like. Let's look at the plots r equals theta from 0 to pi over 4. Sorry, 4 pi. Bam, spiral. Look at the feature on that spiral, how it comes in at a tangent angle. So these are perfect plots. Okay, any questions about that?
No.
Sounds good. Let's look at the equation x squared plus y squared equals 4xy. And let's try and write this in terms of polar coordinates. So in this direction, it's sort of easy because we know what x and y are in terms of, remember that if we had r comma theta, then what did x and y become? So if I wrote this in terms of Cartesian coordinates, what did I get? What were the formulas? So, okay, to remind you, I'll just scroll up to the place where we saw it. So what was the formula? X and Y become what? So R cos theta and R sine theta, right? So this is how I would write X and Y in terms of R and theta. So then if I have a polar equation in Cartesian coordinates, I can write what it is in polar coordinates. I can replace X with R cos theta. So R squared cosine squared theta. Plus R squared sine squared theta. So squared equals 4 R squared cos theta sine theta. Does everyone see how I got that equation? Well, I could write this as R to the fourth cosine squared theta, because there's a square outside, plus sine squared theta squared. And what can I rewrite the left-hand side as? What's this term? What does cosine squared plus sine squared equal to?
One.
Yeah. So this is just R to the fourth equals 4 R squared cos theta sine theta. By the way, how can I rewrite cosine theta sine theta? Let's remember 2 cos theta sine theta equals to what? So this is one of the double angle formulas. Is it for sine or cosine?
Cosine.
No, cosine we've used a
Sine.
lot in integrals. It's the sine one. So cosine of 2 theta is equal to cosine squared theta minus sine squared theta. Whereas if you have a cross term, then it's the sine formula. So I could rewrite this as 2r squared sine of 2 theta. And so dividing by r squared gives me that r squared is equal to 2 sine 2 theta. So we can solve for this. This has a solution. Only when sine of 2 theta is greater than or equal to 0, right? Because if sine of 2 theta is negative, then it can't equal to a square. Now, for example, 0 is less than or equal to theta is less than or equal to pi over 2, and 3 pi, wait, I want pi is less than or equal to theta is less than or equal to 3 pi over 2. I get basically the curve r equals the square root of 2 sine 2 theta. And before we plotted what r of sine 2 theta looked like, right? So taking the square root of a number less than 0, smaller than 1, makes it a bit bigger. So it's going to be a bit of a more round circle, but only 2 lobes of it. So it's going to be related to the plot that we had before, but it's going to be a bit fatter on those ranges. So it's going to look slightly fatter. And it's going to have outermost thickness of root 2. And it's only going to make sense for these lobes plus additions of 2 pi because of this square root condition. So from polar coordinates, we can plot this function. In Cartesian coordinates, how would you ever go about plotting this? This looks terrible. Well, it turns out that this equation defines a shape that looks like this. Figure 8, an infinity symbol. And then I can go to Wolfram Alpha and I can show you a perfect plots. So let's look at the function that I had before in terms of Cartesian coordinates. Equals 4xy. So this is the Cartesian coordinate plot. And then I get this plot, and it's the figure that I drew before. Now let's just check that we got the right plot for polar coordinates. In polar coordinates, I had the equation r squared equals 2 sine 2 theta. And if I look at the plots, I get exactly the same thing. So our conversion was correct. Isn't that nifty? Okay. Well, we have 3 minutes left and everyone is pretty tired at this point, and I've just finished this example. Well, I finished it, so I should put my customary black box. And are there any questions?
So the second half about the plotting is not going to be on homework number 4, right? You said it's going to be on the next homework.
Yeah, actually, we can take a look. Let me quickly pull up the homework and I can make some comments on it. Also, let's see, I have a chat message. Okay. Yeah. So if you look at it, I spent a lot of time on this homework. I think that this is a good homework and these are really good problems. So if you look at it, you have question 1. This is going to be a case where the graphs cross. So you have to divide it into 2 regions when one function is bigger than the other, right? Then here we have a region that you can integrate with respect to x or with respect to y. And we did an example very similar to this in class. So if you do it in x, you have to split it into 2 regions. If you do it in y, you just have to find the inverse functions. Then I give you 2 volumes of revolution around the x-axis and the y-axis, and then these are easy functions. These give easy integrals. They're just going to be polynomials, right? And polynomials are easy to integrate. Now you have 2 problems where you're actually asked to find some serious geometric thing, and these are going to involve integrals where you're doing trigonometric substitutions. So here are 2 serious problems, and here are pictures of what you're asked to do. And then I mentioned, for example, you know the value of arc sine 1/2, but I already told you it. But it's going to come up in this problem. Then 2 arc length problems. And then, as I promised, there are some problems for you to practice your integration skills. So they're the same tricks as before, no new tricks, except that they're now definite integrals. And you have to change the bounds when you substitute. So it's also practice in definite integration. And I mentioned this at the beginning of the assignments. Some of these problems are practice on performing substitutions in definite integrals and changing the bounds. So I think this is a great assignment, to toot my own horn. I spent quite a bit of time on finding these problems. Okay, any other questions? So I think that there are exactly 2 topics left to wrap up this course. I'll finish polar coordinates and then finding areas and arc lengths of polar coordinates, maybe arc lengths, but we're going to do finding areas of polar graphs. So if we, for example, look at this figure, we're going to ask what is the area of this figure, and we're going to be able to do that. And the way that we're going to derive the formula, I mentioned that there are 2 non-trivial formulas that we're going to do. And we're going to do it in a physicist way. So we're also going to write some approximation, and then we're going to get an interesting formula that's not at all obvious for what the area is in terms of polar coordinates. So that's the next time. And then we're also going to discuss what are called improper integrals, which are integrals when the function isn't continuous over the closed interval. Secretly, by the way, we did one improper integral today. And I did this in a way that if you look at this function, the function that we're integrating, the derivative, it's actually not continuous over the entire closed interval when we were calculating the circumference of the circle. It blows up at both of the endpoints. So this is secretly an improper integral. And if you're doing improper integrals rigorously, you need to take limits. And so that's what we're going to discuss on Tuesday. So secretly, this integral was actually an improper integral. Right. Although maybe you could justify it with FTC. And so those are going to be the last 2 topics. And then I'm going to wrap up all of the material on Tuesday. Maybe. I can't necessarily promise that. And then I'm probably going to use Thursday as a review lecture, because I could do extra material, but it wouldn't be part of what's usually covered in the course. So do people prefer me to do extra material? I can talk about complex numbers, for example, or do you want a review lecture? It isn't going to change what I do on the final exam. Review lecture. Okay, 1 vote for review lecture. Any other votes for other things? So next Thursday is the review lecture plus whatever I didn't get to this time. Okay, and a bunch of people have left. Well, that sounds like a wrap. The homework is going to be due, let's say, Wednesday at midnight again. And okay, see you on Tuesday.
Thank
And
you so
hopefully I'll
much.
grade the midterm.
Have a
Bye.
good weekend.
Likewise.